Welcome to this lecture. We're going to today talk about counting principles. In the last lecture, we looked at sample spaces and the potential of equal likely outcomes as a way of defining probabilities. One problem that we run into is sometimes the number of possible outcomes is very, very large. And so we need some rules to allow us to count up the total number of possible outcomes. And once we have that, then we can, if we assume equal likely, we can figure out what the probability of each possible outcome is. It would just be the 1 over the total number of possible outcomes. So we're going to talk today about basic counting principles. How do we count up numbers of possible outcomes? So basically, as I mentioned, if outcomes are equal likely, we really just need to know how many outcomes there are in order to assign probabilities. There's quite a number of different counting methods. A fairly simple graphical approach is the tree diagram. An example of that is our 3-coin toss. So we toss the coin once, we get either a head or a tail. On our second toss, we can come out this branch or come out this branch. And again, we get either a head or a tail. So for the second toss, there's 4 possible outcomes. And then we could come out each of those branches, and again, the next toss, we have 2 outcomes for each of those branches for a total of 8 possible outcomes altogether. The tree diagram is useful if it isn't too complicated. If you've got many tosses or many possible outcomes at each stage, the tree diagram becomes less easy to draw. So it's basically based on the so-called multiplication rule, which goes as follows. If an experiment consists of k stages, and for stage 1 there are m1 outcomes, for stage 2 there are m2 outcomes, and so on so forth to mk outcomes in stage k, then the total number of possible outcomes is the product, m1 times m2 times ... times mk. So n is equal to m1 times m2, so on and so forth to mk. So product of the possibles outcomes for each stage. We saw that back here. There's 2 possible outcomes here, and 2 possible outcomes here, and 2 possible outcomes here. So 2 times 2 times 2 gives us the 8 possible outcomes for the 3-coin toss. I usually show this as using dashes for each stage. So if I go back up here, each of these stages, each of these stages, there's stage 1, toss 1, toss 2, toss 3, and they've each got 2. So I just show dashes for each stage, put the number of possible outcomes in each stage on top of the dash, and then multiply them all up to get the total number of possible outcomes. Okay, so let's illustrate this with an example. 2.8, if we use digits 0 through 9, how many 4-digit combinations can be made? In this case, there are 4 stages for each of the 4 digits. That means I've got to write 4 dashes. And then I just have to figure out how many possibilities do I have in each of the dashes. So there's some sub-questions here. If the first digit is a 1 or a 2 and all digits are unique, this is called sampling without replacement. So they're unique. It means I cannot have a 3 and a 3 in anywhere in it. So I can't have a repeat of the digits. If I think of this as being digits 0 through 9 thrown into a basket and I pull them out one at a time without replacing them, I cannot get multiples of any of the numbers. So the first digit is either a 1 or a 2, so that means that I have 2 possible outcomes for the first digit. Okay. Now once I've extracted one of those digits, I have now 9 digits left in my pile. So the next possibility is there's 9 possibilities. Once I've taken that out, I've got 8 digits left, so I got 8 possibilities for the third digit, and once I've taken that, I've got 7 left for the last digit. And so 2 times 9 times 8 times 7 gives me 1,008 different possible combinations. I could ask if the first digit is a 1 or a 2 and digits may be repeated, so this is sampling with replacements. So basically I said, okay, the first digit either 1 or 2, But every time I do this, I'm sampling from all 10 digits. Then I know my first digit is good. My first digit is either 1 or 2, so there's 2 possible outcomes there. But now I can sample from all 10 every time now. So I get 10 possibilities for the remaining 3 digits. So 10 times 10 times 10 is 1,000, times 2 is 2,000. We could also ask, how many ways can I line 6 people up? Well, it's a lineup of 6 people, so the very first in the row I have a choice from 6. Once I put that person in place, there's only 5 people left, so the second person is selected from 5, third person from 4, fourth person from 3, fifth person from 2, and now there's only 1 person left, and they are at the end. Multiply these things together, 6 times 5 times 4 times 3 times 2 times 1 gives me 720, and this, as it turns out, you've seen this before, I'm sure, is 6 factorial. Okay. We could ask then the question, if 2 of the people are friends and want to stand together, how many ways now can I organize this set of 6 people? Well, if I've stuck 2 of the people together, then I can think of them as being a single unit. And now I basically have 4 people plus this unit, so 5 people altogether. So I'm arranging 5 objects in a row. So basically I know that I can select from the 5 for the start of the line, and then 4 left for the next, 3 left beyond that, 2 left, and 1. The only difficulty is that if you multiply this out, it only comes to 120. And the thing we're missing is that those 2 people can stand either person 1, then person 2, or person 2, then person 1. So I want to multiply this whole thing by 2 for those 2 orientations of the 2 people. So that gives me 240 possible ways to stand the 6 people together when 2 people want to stick together. Now let's suppose that the 2 people have a fight and now refuse to stand next to each other. How many ways do we now have to organize these people in a lineup? I'm not able to figure out an easy way to use multiplication rule here, but I do know that the 720, which is up here, the 720 is the number of ways of organizing them without regard to anybody sticking together. There's 240 of those ways have them together. That means 720 minus 240 is the number of ways where those 2 people are not together. So the way of getting this is looking at the total number of ways of organizing them, subtracting the ways in which they're together, and that gives me 480 ways where they're not together. Now the multiplication rule leads to some special cases that are very commonly used. The first one we're going to call permutations. And this is an arrangement of distinct objects. So these objects you can tell apart. And a permutation differs if order or content differs. Okay, so the important thing here is the order differs in a different permutation. So the number of ways to permute R objects selected from M objects is, and I'm going to use the notation P superscript M subscript R, is M factorial over M minus R factorial. So, for example, the number of ways to arrange 6 people. In this particular case, because usually people are interested in what order they are in the lineup, order matters. So this is going to be a permutation. And we're looking for the number of permutations of 6 people selected from 6. So plugging that into the equation here, we see M is 6, and we're going to select 6 objects, so R is 6. And that means P66 is 6 factorial over 6 minus 6 factorial. And just remember that 0 factorial is equal to 1. And 6 factorial we've already seen before is 6 times 5 times 4 times 3 times 2.1. And that's 720, which is exactly what we had earlier on in this question. 720 ways of lining 6 people up. Okay, another special case is combinations. This is basically the same as a permutation, except that we no longer care about order, just content. So in order to obtain a combination, we have to divide by the number of permutations. We have to divide the number of permutations by the number of ways to order those R objects. So we know the ways of ordering R objects is R factorial. So we take the permutation, which is this part of it, m over m factorial, and divide by R factorial. So we're going to call this, I usually use this format here, brackets with m over R inside the brackets, no division bar, and I say this is m choose R. So we're choosing R things from m, and the formula for the number of ways of doing that is m factorial over m minus R factorial times R factorial. So here's some examples of that. And how many ways can I select two letters from the letters A, B, and C? If order matters, then I can enumerate this. I've got AB, BA, AC, CA, and BC, CB. So there's 6 possible ways. We use our formula where we're selecting from 3 letters, A, B, and C, and we're selecting 2 of them. So R is 2, M is 3. So the number of permutations of 2 selected from 3 is 3 factorial, or 3 minus 2 factorial, which is 3 factorial divided by 1 factorial, which is 3 times 2, which is 6. And that's what we see over here. If order doesn't matter, then AB is the same as BA, AC is the same as CA, and BC is the same as CB. So we end up with just 3 possible contents for this problem if order does not matter. Using our formula, n is 3 choose 2, so it's 3 factorial over 3 minus 2 factorial times 2 factorial. That gives me 3 times 2 over 2, which is 3. Okay, let's look at another example. Suppose you are randomly dealt 13 cards from a deck of 52 cards. What is the probability that they are all spades? Well, I guess the approach to this problem is, first of all, find the number of possible outcomes in your sample space. And our sample space is going to be basically the set of all possible sets of 13 cards. We don't care about order because that's not what we asked. We just asked for the probability that they're all spades. The probability that they're spades in a certain order is going to be a much lower probability. But we're just interested in what is the probability that they're all spades. So this is going to be a combination. We're selecting from 52 cards, so M is 52, and we're selecting 13 of them, so R is 13. So the number is 52 choose 13. Well, that gives us 52 factorial over 52 minus 13 factorial times 13 factorial. 52 minus 13 is 39, so basically we can cancel stuff out here. On top we've got 52 times 51 down to 1, but this 39 factorial cancels everything after 40. So this thing will disappear if I just multiply the top 52 times 51 down to 40. But I'm still left with 13 factorial underneath. Okay. And nevertheless, 52 times 51 down to 40 divided by 13 factorial is still a gigantic number. What's this? 635 billion. So there's 635 billion possible combinations of 13 cards out of a deck of 52 cards. And that means the probability of getting any one set of 13 cards in any order is going to be 1 over the number. So 1 over 635 billion, which is about 1.6 times 10 to the minus 12. A very, very small probability, which is why you would almost never get dealt a hand of 13 spades unless somehow or other the deck of cards was not properly shuffled. And we're making the assumption here that the set of 13 cards are all equal likely. And that means basically that the deck of cards is shuffled properly. Here's another example, example 217. Engineers at college A have 1 student representative from each of the 7 engineering majors. These are biological, civil, electrical, industrial, materials, mechanical, and mining. From college B, we have 1 student representative from each of their 5 engineering majors, and both of these colleges are in the same province. So in how many ways can 2 council members from each of the 2 colleges be selected for the Premier's Council? Okay, so basically College A has 7 members from this council, and College B has 5 members from this council. and we want to select 2 from each. And then the question is, how many ways can we do that? So basically we can use the multiplication rule. Selecting 2 from the 7, we don't care about order, so this is going to be a combination. So the number of ways of selecting 2 from the 7 of college A is 7 choose 2. Selecting 2 from the 5 from college B is going to be 5 choose 2. So the total number of ways is going to be 7 choose 2 times 5 choose 2. And I just put in the numbers here, 7 factorial over 5 factorial, 2 factorial, and 5 factorial over 3 factorial, 2 factorial, and I end up with 210 different ways of forming this Premier's Council consisting of 4 members. Okay, and that concludes that lecture.